Hello, my name is Nikolai Evchenko. I'm Associate Professor in Space and Plasma Physics at KTH. I will introduce you to the course in plasma physics that I teach. Plasma is quasi-neutral gas of charged and neutral particles exhibiting collective behavior. The subject deals with properties of matter in the ionized state, which includes complex interactions of atomic, electromagnetic, and gas dynamic processes. Physics of plasmas is an interdisciplinary field linking to large parts of classical and modern physics and electrical engineering. Most of the visible matter in the universe is in the plasma state. On Earth, plasma is rather an exception, occurring naturally in the upper atmosphere, fire, flame, and lightning, and in multiple man-made devices, for example, the fluorescent lamp. Plasma physics is thus the basic science for space physics, nuclear fusion, and industrial applications. It is an active research area with extensive international collaboration. KTH is known worldwide by the name of Hannes Alfvén, who received his Nobel Prize in Physics in 1970 for his discoveries in magnetohydrodynamics. His work was pioneering in plasma physics and space research. He was professor at KTH, and the building where we work is named Alfvén Laboratory after him. KTH has a strong combination of fusion research, space physics, and applied plasmas, which is rather unique. The foundations of plasma physics are simple. In ionized state, some of the charged particles, electrons and ions, can move about freely. Their motion is strongly affected by the electric and magnetic fields. However, as the particles move, the distribution of charge density and electric currents also change, which in turn changes the electric and magnetic fields themselves. One speaks of collective behavior of plasma. In the classical case, the behavior of plasmas is described by Newton's law for the particle motion and the Maxwell's equations for the electromagnetic field. The complexity arises in the huge number of particles involved and the self-consistent nature of the solution. It is fascinating that plasma objects across a huge range of temperatures and densities show behavior which is very similar and is described by plasma physics, ranging from cold and tenuous plasmas in northern lights, solar wind and planetary nebulae, through man-made applied plasmas to interior of the sun with hot and dense plasmas. Same properties are seen. One of the major drivers for the development of plasma physics is the quest for thermonuclear fusion. This is a process powering the sun, in which light nuclei are merged into heavier and excess energy is released. Just a few grams of fusion fuel available in plain water is equivalent to tons of coals in terms of energy. To achieve fusion on Earth, one needs to heat the matter up to temperatures of millions of degrees to overcome the repelling potential of the nuclei. At this temperature, the matter is fully ionized and is in the plasma state. Confining the hot plasma is a challenge that pushed for the development of this field. The most promising concept right now is confining the plasma in a toroidal magnetic field configuration, so-called tokamak. Currently, a large facility which will demonstrate fusion power, the ITER reactor, is being constructed in France as a wide international collaboration. So what is the course about? As an introductory course, it aims at giving an overview of various areas of plasma physics and at giving students the tools necessary to work further. We discuss occurrence of plasmas with several examples of how equilibrium and non-equilibrium ionization can be maintained. We proceed then to discuss motion of single charge particles in magnetic and electric fields in configuration of various complexities. And then we also discuss the collision processes between the particles. The knowledge is combined to discuss the physics behind electric discharges, which are widely used in plasma applications. As it is practically impossible to have a description of motion of huge number of individual particles, one has to resort to statistical methods in describing plasmas. The hierarchy of these methods is described starting with the most fundamental kinetic description, where the distribution function is described in position and velocity space. If the velocity distribution is of no interest, one can use simpler models which treat plasmas as continuous fluids. Finally, we discuss the topic of waves in plasmas. Due to complex electromagnetic interactions, plasma can support multiple wave modes, which are important both for diagnostics and manipulation of plasmas. Throughout the course, examples of plasmas are described and analyzed, from applied plasma, space phenomena to fusion. You will get the chance to visit the plasma confinement experiment we have here at KTH in-house, the X-trap T2R reverse theta pinch, where frontline research is done on active suppression of plasma instabilities. This work directly contributes to the ITER development. The course is based on a number of lectures, some of which are given by guest lecturers to cover specific topics. Examples are treated in the problem classes. Also, the course includes a session on computer modeling of plasmas, where you get to work with MATLAB codes addressing plasma physics from numerical simulation perspective. Finally, there is an individual literature study where each course participant will work with original research papers treating a narrow topic related to plasma physics, and will later present this in class. This was a quick introduction to the course in plasma physics which I teach. I'm looking forward to working with you in the course.